Hi. Last time I made a 2D version of grayscale image implemented in Houdini. So this time I would like to show how you can extend that 2D grayscale image to 3D. Simply, the base implementation is pretty much the same. The only difference you would have to do is the laplacian functions, which in 2D grayscale image it's 3x3 convolution, but when it comes to 3D it's 3 times 3 times 3 convolution. So that's the only thing you have to change within the code for the grayscale image, grayscale pattern for 3D. All the other stuff, like these parameters and stuff, can be used as it is. So let's try that. Also the difference is that when you use 3D, the resolution or the pixels, or should I say voxels, that you're gonna use is exponentially increases because of one extra dimension. So you cannot, well, you could, but you cannot really use high res like 500 by 500 by 500, since that's really huge for calculations. So I would suggest you go with the lower resolution first. Then if you like that pattern, then you can increase that later and maybe stay overnight for the renderings. Okay, let's first make a geometry. I already did. And first of all, what you need is a bounding box. So let's make a box and decide the size first. Okay, I can set the size with the parameters. So let's make a null first and name this controller. Color this and make some parameters here. Now some of the parameters are much similar to the one that I made for the 2D grayscale image. So if you haven't watched it yet, I would suggest you watch that first, then go back to the 3D version. Then you can understand more. Okay, first of all, let's set the size, and also, since I'm gonna use the a volume, a voxel, I'm gonna set the resolution for that. So let's say res from 0 to something like 100, and also let's set the number of initial pattern, which I'm gonna make with the sphere pattern. I'm gonna say init num. Okay, and from 0 to 10 is fine. And also the size of those initial spheres could be from 0 to, I don't know, 1. Okay, and also for the grayscale pattern, I need a parameter f, which is for activator. And the, how do I say, the appearance or birth rate for the activator, and the k, a kill rate for the inhibitor. I guess from 0 to 0.1 is the range for these. and a dA and dB, which is a diffusion rate for the activator and inhibitor. A is a activator and B is the inhibitor. Okay. And finally the speed for the diffusion, delta from 0 to 1. Okay, that's it for the parameters, and accept. Let's set some size first. Size will be 10. Resolution, I could try with 50. Num 10. Init size 0.8. 0.04. 0.06. And well, this could be 1.5 and delta will be 1. Okay, now I could just change this later for the different pattern, especially F and K, which is critical for changing patterns. Let's go back to the box and let's copy the size from the parameter and paste it into uniform scale. Okay. And let's transform this a little bit. Scale this a bit smaller. To have a boundary for positioning the initial sphere's initial pattern. So I'll make this like 0.65 and make it volume using ISO offset. Yeah, probably to 50. Resolution to 50, and using a scatter to scatter the point, but that right now it's too much, so I'm gonna copy this init num parameters here and paste it into the force total count so that I have right now 10 points. Okay, now after I got this point, I would like to copy the sphere to those point positions. So let's make a sphere, and for the size of the sphere, it's this one, and its size parameter. So copy this, paste it into the uniform scale for the sphere. Okay, and use the copy stamp to copy the sphere to this scatter points. Okay, great. Now finally let's convert this into the volume. Now the resolution is a bit low, so I would like to use the set the resolution parameter into this uniform sampling divisions. Okay, that looks better, and I also would like to set the boundary, since right now if you look at it, the boundary is not consistent, like 45, 50, 46. So to make it 50, 50, 50, I can connect this box to the reference bounds here, which didn't really change the number here, but it should give a boundary of 50, 50, 50, which could be used later on, which I'm guessing you might not need this one, but I'm just gonna go with this. Okay, now since I'm going to have two types of particles. One is A, one is B. A stands for the activator, which goes around and being added at some ratio. And there's B, which is an inhibitor, which eats up this A, particle A, and at some ratio it will kill himself. So there's two, A and B. So which means I need two volume values, A and B. So I have to make two volumes. One, the name of A. Well, let's name the default one to density here. And the default value is fine. I just need to change the sampling division, which should be the same as the this resolution. So I'm gonna copy this resolution parameter from the controller, paste it into here. Yep, and that's for the A. And I also need B. So by doing this, I could have two volumes, and if I merge this, you'll have two volumes attached to each other into one node. Oh, geometry. Not really geometry, I guess. Okay, well, next thing I would like to do is use the volume wrangle to set the initial value for the A and B. Okay, right now it's just empty since it's 0, 0, 0. So for the B, I would like to plot the position of the circle, and A is the invert of that value. So let's bring the ISO offset value, which is this one, to the second input here, the volume wrangle, and bring the volume A to the first input like this. Okay, and let's write some simple definition. So the A should be 0.1 minus volume index from the input 1 and index 0 set something like this. Now you can see the values on the sphere position are cropped out of the white bound. Yeah. Should be okay. Now let's go to the next one. For the B, you just need to do the opposite calculation. Just copy this and connect B to the first input of this one, and density B is just a volume index. Okay, that's good. That's good, I think. Well, volume index means that get the volume at specific index, which the index is this one. So it just means it's just copying those value to here. Oh, and I guess I need to set the size the same size as this one. So let's copy this size parameter, copy, and paste it into here. Paste reference, and paste. Okay, and this one as well. Paste, paste, and paste. Now let's look at the result. Yeah, looks correct. So let's go with this. And now I have two values A and B. Let's merge this together. And if I look at it, I have volume A and volume B with the boundary of 50-50-50. That's cool. Okay. And this is where you're gonna use the solver to calculate the Gray-Scott 3D pattern, which is pretty much the same with the last time, the 2D version. So give a volume Wrangle instead of the point Wrangle, and let's write some code. I'm gonna open up the window here. Okay. Now, first of all, what I need to do is make a function to get the point index or voxel index. I'm just gonna name the same function name as the 2D version, but in this case you need U, V, and W, since you have 3 dimensions. And the size can be retrieved from the obj GO1 controller resolution, which is the resolution size, and the index of that volume from U, V, and W, which is the range is from 0 to 1, could be calculated like no, it's not really 0 to 1, it's from 0 to 49, because I set the size to 50 for each U, V, and W, X, Y, and Z. So the total index, which is in 1D, is U times size plus size, V times size plus W. Return index. Okay, that's the function for getting the index of the volume, but I am not sure if I'm gonna use this. Maybe I don't really need this. Yeah, probably not use this, because volume itself has a good function to get the index, or you don't really need to use the index, I guess. See it later. Okay, vector 2. So the things that I need for other functions that I need is the Laplacian function for the 3D, which is a bit different from the 2D version. So I'm gonna name this Laplacian 3D. The input is u v w float center, float adjacent, float diagonal, and float corner. Okay, and the size you wanna get from the obj go1 controller resolution. Okay. Now the output vector 2 means that which will be the value a and b. The a comes to the x value of the vector 2 and b value comes to the y position of the vector 2. The result of which is the result of the Laplacian calculation. So let's make a default vector 2 value here. Call new lap. Like this, and let's iterate through 3 by 3 by 3 convolution by starting from -1 to +1, and I'll just copy this and change the second for loop value to n and the third one to be t. Okay, now let's make conditions so that it will only calculate within the boundary, is not on the boundary, so, or outside a boundary. So if u plus I is less than 0, or u plus I is larger than size, or v plus n is less than 0, or v plus n size, or, okay, gotta make it longer, w plus t is less than 0, or w plus t is larger than size. Just do nothing. Else get the float value a from the volume index 0 a. Yeah, I want to get the value a, which from the volume a and at this position. Now volume has the function called volume index itself, so I really didn't need this function, which I have used for the 2D, but 3D have more useful stuff function, so just gonna use that one. And value b, volume index 0 from b, set u plus I, v plus n, w plus t. Okay, so the temporal Laplacian value, use the set value a and value v. Okay, now here comes the laplacian valuing here. So the 2D convolution, for the 2D laplacian, you have center weight, adjacent neighbors weight, and diagonals weight. But for the 3D, since you have 3 by 3 by 3, you're gonna need one more options, which is a corner position. I'm gonna show you with this box. So there's a center, correct? Yeah. And adjacent will be the point which connects to the position with its. I'm just gonna draw it. So if you have all the box. This is really ugly, but let's say this is the box and you have 3 by 3 by 3. And if you look from the center, the adjacent point will be those one, which in total you have 1, 2, 3, 4, 5, 6 adjacent. Now, what else? The diagonal. For the diagonal value, which is this one, you have the place for the diagonal will be here, 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 here. Which have the same distance from the center to those diagonals. And in total you have 12. Or, yeah, 12 diagonals. And last of all, for the corner, you have here, oops, here, here, let's make it green, here, 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 and here. So in total you have 8 corners. And finally you have 1 center. So you have in total 27 points here. So it's by 3 by 3 by 3. So each 6 adjacent, 12 diagonals, 8 corners, and 1 center should have different values, values for the Laplacian calculations. And if you add all those values, should become 0. So let's keep that in mind. Let's make that. So if I equals to 0 and n equals to 0 and t equals to 0, this means the point is in the center. So new Laplacians will be added with the Laplacian times center parameter. Okay. else if absolute value of I plus absolute value of n plus absolute value of t, and moduled by 3 is 1. Then this means that the point is on the adjacent position. So new lap times adjacent. Else if and absolute t module 3 is 2. This means the point is on the diagonal positions, so I'm gonna use the diagonal parameters to calculate the new laplacian value, and else this should be the corner. Okay, and finally return the updated new rep vector 2. Now that's the function that I'm gonna use for the laplacian calculations. And now I need to the actual calculation here. So let's retrieve the A value, B value, F parameter from the controller, F float K equals CHF, float dA equals CHF, float dB equals CHF, dB, oops, float delta CHF delta, and vector 2 Laplacian AB will be retrieved using the get Laplacian 3D, which I have just made on the Ix, Iy, Iz, which is the x and y and z index for the volume, each volume. And for the values, okay, well, the total, since I have to make all the values, if you add all the values together, it should be 0. So for the center, should be -1. And okay, for those, the adjacent, I could go like 0.2 divided by 2.8. And for the diagonal, 0.1 divided by 2.8. And for the corner, 0.05 divided by 2.8. Which means if you look at this one, so this means 6 times 0.2 plus 12 times 0.1 plus 8 times 0.05 equals to 2.8. So all the mass addition result will be 1. So by adding -1 plus 1 should be 0. So that's how I made this parameter here. Now with that I should get a result for the A and B. So oh, and the Great Scott mathematical function looks like this one, so I'm gonna make the variable for A times B, which is used for both equations. So I'm gonna name it reaction, which is A times power B2. Okay, now let's update the A and B. So dA times laplacian AB A at 0 minus reaction plus F times 0.1 1.0 minus 1 and delta multiply by delta. Okay, now the B will be dB times Laplacian AB index of 1 plus reaction minus K minus F times B and multiply it by delta, which is the speed of the diffusion. Okay, apply. Let's see if there's no errors. Seems okay. Accept. Now that's all you need for the calculations. And let's go back here. Oops. And actually, I'm showing both A and B here right now, so I'm gonna use just one of those, float A, density A or density B, to actually visualize it. Now for those for this one, I think using a B value is easier to see what's going on with the 3D. So I'm gonna delete the name A and just get the B density here. Now let's play to see if I get anything. Now I did get something, but something seems wrong. Yeah, this seems a bit wrong. Shouldn't go like this. Okay, let's go back and see what's wrong. Let me pause a little bit to see. Okay, I think I know what was wrong. If I look at the calculations for the second equations, it says K plus F, but I wrote K minus F, so it should be K plus F. Okay, and if I play this, okay, something is happening here. Yeah, something is happening here with the voxel, with the volume. Now what I need to do next is to actually visualize this to see if I'm really getting the Great Scott pattern image. Now I guess I would like to convert it into polygon as a final result. So before doing that, let me give a volume wrangle to a little bit clumping the value a little bit. So right now I'm dealing with the B value, so I'm gonna modify this using the ch ramp and click this to give a ramp parameter here, and let's try controlling this to actually modify the value here. Yeah, I think I am having some pattern here, which looks a bit interesting. Now let's visualize this. Thing I could do is convert VDB, and from fog to SDF. Okay. And also let's use the convert VDB to convert from VDB to polygon. So right now this doesn't give me anything, so let's bring this a little bit to the left. And yes, I'm having something here. Now this could be a good position. Let's keep praying. Yeah, I'm having some interesting reaction here. Now the resolution is right now 50, so it's a bit low res. So what I could do, I could simply increase the resolutions. Right now it's 50, so if I increase it a little bit more, it should give me more high res image, but also the calculation time will increase exponentially as well. Let's say if I want to make it 50 and try calculating it. I'm getting something faster. I might need to increase the solver step for this one, but I can see something is happening, some reaction is happening here, and it looks pretty promising. So let's increase the sub steps to like 5. Yeah, it's indeed a bit slow compared to the 2D, but the result is more interesting from what I see. Now let's keep this a little bit. Yeah, it's getting more and more complex with the time. Seems like it's trying to close up the boundary. I might wanna cut the outer bounds so that I can clearly see what's happening inside. Because right now it's hard to see what's going on inside with this one. Yeah, so let's pause this a little bit. And let's make... Okay, well, I have this box here. So let's bring this box connect to the null and bring to somewhere around here until the before converting to the VDB. And I'm gonna use volume mix and mix those. Oh, guess I could. Okay, I guess I could copy this resolution parameter here. No, I'm just gonna make a new one. ISO offset and paste the resolutions here. And with the volume mix, I'm gonna use the minimum, which should cut out the volume with this box. And let's visualize this one. I guess I need to transform, scale down a little bit more. So I'm gonna transform the base box, bring it here, and like 0.6, 0.65, 7, 7.5, 8, 9, 1 was not okay, so 0.95. Okay, now could be like 9. And let's use this to fine tune a little bit. Okay. And the edge looks ugly enough, so before converting to the polygon, I would use the VDB smooth SDF to smoothen out a little bit. With one iteration is fine, I guess. Yeah. And that's it. This is the result with the 3D grayscale pattern. And looks pretty interesting from what I see. And you can choose the boundary where to volumetrize or polygonize using those ramps. Yeah, interesting. And if I keep playing, it will try to grow more, I guess. Okay, now I would like to show you one technique in order to color this volume using the volume attribute, volume density. So after converting this from volume to VDB or to polygon, you will lose all the attributes for the volume value. So you'll not be able to, at this point, you cannot use volume in order to, for example, color this stuff. But if you use a component called node called volume attribute from volume node, and for the left hand side, connect the final output here, and to the right hand side, connect the volume which has the values that you want to apply to the attribute, point attribute, which should be this one. I will connect here, and now you can see you're having, when I can change the parameter here, so the attribute here, so I'm gonna set to the col with the attribute size 1, and if I look at the geometry spreadsheet, you can see the value b is inserted into the col attribute like this. What if I connect this here? No, this doesn't work, so this is fine. Now after this, you can just use that col attributes to color, probably. So ram from attributes and set the col, and move this a little bit to the right, move this to the left. Yeah, somewhere around here. So the darker it is, the less b value there. The lighter it is, the more b value you have. So you can kind of see the analyze the geometry, the grayscale pattern image, by using the color. Now let's make the color a bit more interesting, like blue. Yes, looks good. Make it more darker. It's fine. Okay. And let me make a flipbook, and I'll finish this. Now, if you go back to the parameter and change the f and k as I did for the 2D, you can also see several patterns for the 3D grayscale. So I suggest you play with that. Let's make a flipbook. Start. Okay, that's it. Let's play. Okay, thank you.